And coming back to today's webinar, we are very pleased that all of you from all over Europe could make it and are interested in this topic we have today. We have called it a microscope for molecular movies. And in this webinar, we would like to give you an insight into the fastest X-ray source in the world and the kind of research we are doing here, of course. So in the next hour, we will first take you on a journey into the fascinating world of X-ray lasers and the microscopic universe that can be explored with X-rays. And afterwards, we will try to answer all your questions you might have, which you can write in the chat window you can see below. And you can also already start asking questions during the presentations. So now I would like to introduce today's speaker, which is Joachim Schulz, you can see already. He is a physicist and senior scientist here at European XFEL, and during his studies, he specialized in quantum optics and atomic and molecular physics. And after working for a Swedish university, he joined the Research Institute DESI in Hamburg, Germany in 2007. And now, since 2011, he has been part of the European XFEL family. And with this, I would like to pass on to you, Joachim.
Yes, thank you, Sarah. Let me first share my screen. That's this one. Yes, thank you for the introduction, Sarah, and thank you all for tuning into this seminar on the European XFEL. You already see a picture of the main part of the European XFEL, which is also a particle accelerator. But we are accelerating electrons, and we are accelerating them in order to create X-rays, which is a bit different from what you will hear in the next talk by CERN, where they are using the particles for colliding experiments and for particle physics. So that's why I called my talk a microscope for molecular movies, because one of our main interests is to produce movies of the molecular world, movies with very small atomic particles. And for this, we will need an X-ray laser with very short intense pulses. And I hope I can, with this talk, give you an idea why we need these strong and intense X-rays and how we are producing them. And then in the end, I will also tell a little bit about the experiments we are doing with them. But to bring you in perspective, you are sitting all over Europe, and to show you what we are and where we are, I put up a world map here to show you we are here in Europe, in Hamburg, and there are actually a couple of other lasers, free electron lasers, working all over the world, but it's only a handful. We have 3 in Asia, 2 in Europe, and one facility in the United States for hard X-rays, and then a couple of soft X-ray devices on the world. And we are here, the one in Europe, European XFEL in Schenefeld, close to Hamburg. So if you are zooming into Europe, that's where we are. And if you draw a map in the city of Hamburg, you find us on the northeast, or on the west part of Hamburg, on the western edge of Hamburg, and just going out of the city limits of Hamburg. And this is also another federal country of Germany. So Germany is a federal republic, and our free electron laser starts here in the city of Hamburg and goes all the way in underground tunnels under the city of, or the outer rims of the city of Hamburg, into the small town of Schenefeld in the federal state of Schleswig-Holstein. And one reason why we are starting exactly at that point is that this is a DESI Science Campus in Hamburg, where the European XFEL starts. It's here located in Hamburg, about 3 kilometers or 3.4 kilometers from the place I'm sitting in. And this is a long tradition of an accelerator driven X-ray sources. We have the X-ray source called Petra 3, a ring source, and a soft X-ray laser called Flash. And from there, the electrons are starting into the European XFEL, which is a 2 kilometers long accelerator, followed by about 1.5 kilometers producing the X-rays. So what is the European XFEL? It's an ultra-fast, super intense X-ray source. So we are producing X-rays that come in very fast, very short bunches that are extremely intense and that are in the optical range of X-rays. So if you look at this picture, you see this blue glowing here. This blue glowing is actually the X-ray beam, but not because you can see X-rays. X-rays are invisible, as you probably know, but because the X-rays are so intense, they are ionizing the air, so they are drawing away all the electrons from the air. And then when these highly excited atoms are getting the electrons back, they are emitting light, and they are emitting mostly light in the blue region. So that's why we can even see the X-rays. And if you can see X-rays, you already know it's very intense X-ray beam. So, and I'm now trying to motivate, why do we need an ultra-fast, super intense X-ray source? So why should it be intense? Why does it need to be X-rays? And why do we want to be that fast? And when I have done this, I will show you how we actually are doing this. So the electron production, the acceleration of electrons, and how then the electrons are converted into X-rays. And in the last part of this seminar, I would like to give you a little insight into which kinds of experiments we are doing. So I will show you some examples of science that is done at the European XFEL. But let us start with the question: why are we going to be in microscopes? So what's making the European XFEL a microscope? So this is an image I found in Wikipedia about the different sizes of different things. So we are coming from here. This is our world. The sizes humans are in the order of meters. And if you go down via X to the nth in the order of a millimeter scale, to the bacteria in the order of a micrometer scale, down to nanometers, where the building blocks of biology live, so proteins and lipids, and then even down to a tenth of a nanometer called an angstrom, which is the size of a single atom. And so the question is, what do we want to see? We want to see at the European XFEL mostly these really small things. We want to see atoms. We want to have a resolution big enough to distinguish single atoms out of a body or out of a protein. We want to see viruses that are not visible in normal light microscopes, and we want to see proteins. And how are we doing this? Or why can a microscope actually go down into the scale? And what do we need additionally beyond a microscope to even enter the atomic resolution is what I want to show you. So one question I was always asking is, we can see ants. Obviously, we can see things that are 1,000 times smaller than humans. But there is an open question, or it's not an open question. Ants cannot see bacteria, even though bacteria are also 1,000 times smaller than ants. So obviously, this is not scaling. There is a reason why ants can't see bacteria. And there is also another reason why we can see bacteria if you are using microscopes. And this I will bring towards you so that you understand a little bit better why we need the intense radiation of the free electron laser. So this is what you can see with the naked eye. So if you have a good eye, you can see, maybe you can distinguish structures down to 100 micrometer, but you cannot go further. If you want to go further, you are using a light microscope. With that, you can go in the order of 100 nanometer, and we will soon explain why you cannot go further with a light microscope. But first, I want to point out what a microscope actually does in order to be able to see these small structures. And there are two things a microscope generally does. One is it goes very, very close to the object it wants to see. And secondly, it collects a lot of light. Going close, you can see in our lab devices, we have a lot of microscopes here for checking the samples before we go into the free electron laser. And we have labs with all microscopes. And what you generally see is that the objective of a light microscope is very close to the object it wants to actually see. And this is because it wants to collect a lot of light. So you have to go close by. If you are not close enough, there are microscopes that go further away, but then this objective is tending to become bigger. So what we learn from this is to see smaller things, we need a bigger eye, or we need to get very close. And this is basically the reason why an ant cannot see bacteria. It has small eyes. So you need a being with larger eyes to see smaller structures, or you have to go very, very close. And the other thing is we need bright light sources to collect a lot of light. And the reason for this is, of course, if you have a small structure and your eyes are as efficient as your normal eyes, you need much more light because it's less material you are taking the light from. So you need very bright sources. And if you see our scientists here working with microscopes, you will always see that they have extremely bright light sources. So with the naked eye, you cannot see anything here because it's blinding you. And this is because the microscope looks on such small objects that only reflect a tiny bit of light. And with this, I can also already answer the first questions. We need to be super intense to have resolutions to see single atoms, because an atom is not scattering a lot of light. So we need to have very much light to come in order to have enough light to see something to distinguish the atoms. The next question is, or I can show you, the next question is actually, why don't we can we not with intense light source go lower than this 100 nanometers? So we have this microscopes. I already showed you oops, press the wrong button. I already showed you the objective of this microscope. So this is the one you know, and we have regularly days where we invite school students to come to us and play with our microscopes. And what we can easily see is the structures on human hair. So this is about what we can see with microscopes, with light microscopes. And we can see, if we are good, we can see plant cells, we can see bacteria, but what we never can see is viruses that are living here somewhere between a nanometer and 100 nanometers. And the reason for this, you probably have heard of. Light is an electromagnetic wave, and a wave is defined by its wavelength, how long a single wiggle of this wave is. And a light, the visible light, is about an octave. An octave you knew from the acoustic, from music instruments. It's the double. If you are doubling the wavelengths, then you have an octave. And it's actually from 400 to 800 nanometers. That's the size of a visible light. So a nanometer is a billionth of a meter. 800 is nearly a micrometer. It's nearly 1,000 nanometer. That's a micrometer. And this is exactly the reason why we cannot see with optical light. We cannot see anything that is smaller than a micrometer. I can. What I always find very instructive is you try to draw the wavelengths of green light in a scale where an atom is visible. So this is a wave, and this is only a part of a wave. And I assume this is a blown up wave that is about 5,000 angstroms long. So this is 500 nanometer, it's green light. And compared to this, an atom is about this size. So an atom is merely surfing on this wave. So it doesn't see this as a wave, it sees it nearly as a straight line. On the size of an atom, the wave hardly changes. And this is why you can never distinguish a single atom. If here's another atom, it sees exactly the same wave, and you cannot distinguish them. So coming back to my scale, or to my picture here, I think I made it clear that you can only see things until here. So this scale comes from left to right. So the human being is here in the meter scale, and you can see a cell with light, and you can see everything, every structure you can distinguish. This has the size of the light wave, but everything that is smaller than a light wave, you just cannot distinguish. And this is where the virus, the proteins, the atoms, and the nuclei go. And this is why we are using X-rays. So with X-rays, we can go down. The X-rays we have here are tuned in a way that we can go down at least to distinguish single atoms. This is our design goal. This is what we want to reach. You can go even harder with X-rays, and you can go can also go to X-rays that are in the size of an atomic nuclei. But here the physics will be more complicated, and here this is not actually what is easy to see, and this is what you actually would see in the next talk. If you go to the LHC talk, you will see how to make atomic nuclei visible. So we are talking here about making visible what's living here: atoms, DNA from biological substances, proteins, the work force which is working in our cells, and virus particles. This is why we need an X-ray source. X-rays are old. The very first X-rays have been invented about 120 years ago, in the beginning of the 20th century. Wilhelm Conrad Röntgen invented this X-rays, and this is one of the very first images of a human hand. So another thing that X-rays is they can go through soft matter and make the hard matter visible. So this is a living hand, but you don't see the tissue, you only see the bones because it's harder matter, and you can clearly see the ring because this is metal, and this is easy visible for X-rays. I must confess that electrons can do about the same. So we have in our lab electron microscopes that also can see atomic resolutions. They can also go down to this. These are also school students we invited here for working with our electron microscope, and we took a small fly into the electron microscope, and an electron is able to see the structure on the eye of an insect. It sees that the insect eye consists of many very small pupils, and between these pupils you even have a little hair on this eye. So insects have hairs on the eye. You can see this with an electron microscope. The problem with electron microscopes they are slow. So taking an image with this great resolution of an insect takes a minute or two, and this is too slow for doing the second thing, what I wanted to see. So I said we want to see movies of molecular things, and we don't want to see just still images. And for this, we have to become faster. Fast movements can be taken even a bit longer. So in 1882, Edward Muybridge developed this fast photography. And this was in Stanford, where one of the 3 electron lasers I showed in the beginning was standing. So on the west coast of the United States. And he had a bet with some friends. He was a fan of horseback riding, and he asked whether a horse will have all hooves off the ground during the gallop at some stage. This was unclear at this time, and many people thought in this phase where the horse has all the hooves away from each other, it would leap, and so it would jump like a frog. But this is actually not true. If you look at these pictures, this is the phase where the horse has all 4 hooves off the ground. And somebody who was riding, actually also a girl we invited here for a Girls' Day, was telling me this is also the most dangerous part of gallop riding, where the horse is most unstable. So it's actually good to know that this happens. And it's nice to learn how a horse moves. And it's as nice to learn actually how a molecule moves in order to understand how a molecule works. So, but what do we have to do the same? Here, this is a goal picture, which is also used for high-speed photography, where you have a subject that is about 10 meters per second fast. The picture resolution should be in the order of centimeters, and the time resolution in thousandths of a second, a millisecond, is good enough to see who was first on the goal line. If you're now going to high-speed things like a bullet through going through this apple here, you have faster motions. The motion is in the order of speed of sound. The resolution is not that much higher you need here because it's a smaller object. This object is in the order of a decimeter. This object is in the order of a meter. So you probably want to have a little bit better resolution, more in the millimeter range than in a 10 millimeter range. And then you are coming to the fact that you need not 1,000 seconds resolution time, but you need a millionth of a second, which is a millisecond. And now, if we are going to atomic movies, we have the rattling speed of atoms, and this is comparable to the speed of a bullet. And it's not so far away from the movements we are doing. This 10 meters per second is the movement the runners are running, but their feet are actually moving much faster. So it's not so far away from in speed. An atom is not so far away from the normal optical light photography. But what's really making the difference is you need a very good resolution. You need a 10 millionth of millimeter resolution in order to see this atoms. Because if an atom moves millimeters, it's far away. It's not anymore where it was at the first place, and you will not learn anything of this movement, any details of the movement, if you only distinguish the resolution of 1 millimeter. And this is why we have to be that fast, and this is in the order of 100 femtoseconds. This is the speed we need. So to bring this together, what do we need to see the same with atoms? So atoms are much smaller than hoofs, and this is why we need X-rays. I told it again already. Atoms are a bit faster than hoofs, but not so much faster than hoofs. Maybe 10 times, maybe 100 times, but not much more. But they don't move long ways. If an atom moves a nanometer, it's already 10 times made already 10 times its size. So we need to see very tiny things. Seeing tiny things leads to having to have an intense X-ray, but it's also the main reasons why we need to be ultra fast. We need to be femtosecond fast. To remind you, a nanosecond is a nanometer. We are talking here about nanometers, is about a billionth of a meter, and a femtosecond is a millionth of a billionth of a second. And we are talking about 100 femtoseconds. That's a design goal, and this is the normal operation of the free electron laser. We can go lower, but this is what we do most of the times. So how does a European XFEL now produce this these intense short X-rays? For this, the reason why we call it free electron laser, it combines the ideas of having an ordinary light source and a laser. So an ordinary lamp works in the visible range. This is here around. I already showed this picture from the visible octave somewhere in the below a micrometer range. And this is also where normal lasers work. So if you're using a laser pointer, or if you have an intense laser for fabricating things in the car industry or so, they also live in the region of infrared to ultraviolet, and very often visible. If you want to produce ordinary X-ray sources, you are normally going to DESY, the place I showed you where our X-ray, our laser starts. So this is a ring accelerator that produces normal, ordinary light in the wavelengths of X-rays. But if you combine these two, you are coming to a free electron laser, and only free electron lasers can do this 100 femtosecond resolution, time resolution, and they are bright enough to see with just a single shot the complete molecule with atomic resolution. This is an overview of the facility, a little bit different overview than I showed before. We are starting here at DZ Bahrenfeld. This is a ring accelerator I told you about. This is where the ordinary X-ray light is used, and it is used for many very interesting things, including microscopy, but it cannot make movies with atomic resolution. And it starts here. You see also the profile of the Earth. It's going a little bit down towards Schenefeld, so the ring starts about 20 meters underground, and when we are here, we are about 12 meter underground in Schenefeld, in the city of Schenefeld. And I will show you the electron injector, how the electrons are produced. I will show you the superconducting linear accelerator, where the electrons are sped up to a very intense, to a very high energies. This is happening in this long single tunnel. And then here in our first station, in our first vertical building, it's located here, after about 2 kilometers, we are splitting up the electron beam, and we are guiding the electron beam to so-called undulator systems, where the electrons are converted into X-ray radiation. And then finally, on our premises here in Schenefeld, where I'm sitting directly under me, about 12, 15 meters under me, you have the scientific instruments, and I will show a few examples of the scientific instruments. How do we produce the compact electron bunches? First, electron bunches have to be produced, and they have to be a very intense bunch of electrons that are accelerated. And for this, we are using an optical laser. Actually, we are using a laser that is hitting a surface of a semiconductor where the electrons are not very strongly bound to. And by very quickly heating the surface, we can produce a cloud of electrons that is guided by and bunched by a magnetic field, kept together by a magnetic field, and then accelerated in an electric field by a single accelerator module, pulled out of this shortly heated material. And with this, we can create very, very short and very small and intense electron bunches. The electrons repel each other. You all know probably that electrons are charged. They are negatively charged, and everything that is charged the same is trying to get away from each other. And this is why it's so hard to produce a compact, intense bunch of electrons. And this is why we had to have a lot of development in order to produce this injector that can produce really intense electron bunches by heating them extremely quickly with an optical laser, and then using the strong fields to accelerate it as soon as possible, as fast as possible. This is how this electron gun runs, and I can tell you this acceleration helps a lot in keeping the electrons together because of the special relativity. If you have heard about relativity, special relativity theory says that if something is fast, the time for it runs much slower than it runs for us. And this means as soon as these electrons are very fast, they don't have much time anymore to explode, to get out, to get bigger, to grow a bigger cloud. And this is why we have to accelerate them very quickly and have them very quickly on a high speed. And then we are going into the main accelerator things. And this accelerators, the accelerator structure, these are microwave cavities made of neop. So these are just metal sheets that are shaped like bulbs, where an electric field with exactly the wavelengths of the distance here can be kept. And this electric field is then pushing the electrons forward. And I already showed you electrons and atoms and electrons are much smaller than an optical light. And these are microwave cavities. So there the wavelengths of the electric field we have here is in the order of a decimeter. So it's about this size, actually. And this means the electrons see the slope of the electric field when they are in there. They don't see that this is a wave. They see a slope of the electric field. And we are timing the electrical wave that is happening in this modules. We are timing so that the electrons are accelerated all the time, so they're getting faster and faster. So it's like a ski ski rider who is only riding the hill up down the hill all the time, downhill, 2 kilometers long downhill, which is a long distance for an electron that is that small. In 69 accelerator modules, we are moving our electrons, and they are really soon reaching nearly the speed of light, and then they getting as fast as 99.9999996% of the speed of light speed. This is the speed the electrons reach, and since this is a unhandy number, so when does the 6 comes, what we are normally using is an electron energy of 17.5 gigaelectron volts. And the cracks of you who already know a lot about relativity and stuff would compare this to the rest energy of the electron, which is basically how heavy an electron is. So this is 34 times, or yeah, 35 times the energy that is condensed in the rate of the electron, and this makes it so fast that it's running with the speed of light. So this is, of course, this accelerator driving a 2 kilometer long accelerator is, of course, the one source that draws most of the electric energy we are putting into our facility. So about 80% of the electric power our facility drives is used by this accelerator, and a lot of this is of course used because we have to keep this accelerator on extremely low temperatures to make it superconducting. This is how the accelerator modules look like. You don't see much of them because in this yellow bottles you have liquid helium that keeps the accelerator module small, very cold. Because in this cold environment, these neop cavities are superconductors. That means they have no electric resistivity, which means basically that these waves we are putting in there, where the electrons surf on, can for a very long time be stable in these cavities without decaying too fast. And this is the reason why we can produce that fast electrons on 2 kilometers area. And then in the last step, of course, the electrons have to be converted into X-rays, because X-rays is actually what is most flexible for us to do all the kinds of science we want to do. So for this, we have magnetic structures called undulators. These are alternating magnetic fields, a magnetic field going in this direction and magnetic field goes in the other direction, and this alternating all the way. And by this magnetic force, we are forcing the electrons to run in slalom course. And what's happening when an electron runs in a slalom course is it radiates electromagnetic wave. You know this from the antenna of a radio of a walkie-talkie. You have normally a steel antenna, and what this antenna is for, it pushes electrons in and out of this antenna, and these electrons are moving back and forth in the speed of a radio wave, and they are creating a radio wave that is then going away from this walkie-talkie and can be seen or can be detected by another walkie-talkie and reconverted into the speech you are or into the voice you are giving. And this is exactly what's happening. See here, if an electron would jiggle around all the time on one place, it would, or a bunch of electrons, of course it is, it would create a wave that is about the wavelength of the size of the structure here. But and then in a Sarser process, this in a so-called Sarser process, I will explain a little bit later what this is. It creates a super intense radiation. And the trick of this is that we have again a relativistic effect, namely the Doppler effect. This you know from the horn of an ambulance. It sounds much higher in pitch when it comes towards you than when it drives away from you. This is a so-called Doppler effect. So things that approaching the sender, producing a much shorter wavelength than things that are going away from the receiver, of course, going away from the receiver. So this is wrong in the slide. Because the electrons are so fast, they are nearly as fast as light, and light is the speed where the wave is going with. Therefore, these waves are very much compressed, and then they can be compressed into the X-ray range, and this is why we need so fast electrons for doing all this. This is how the undulators look like. So they are big metallic things with big motors, because these magnets here there are the magnet structures. They are, of course, trying to get together, because these are magnets where a North Pole and a South Poles are exactly opposite to each other. So they're trying to push together, and so we need very heavy instrumentation to keep these magnet structures away from each other. We also have the warning signs about magnetic fields, because it's so much power or force these electrons do. And now I come a little bit to the laser principle of the free electron laser. The idea of this is that the same electron bunches here, this blue thing, the electron bunch, when it comes through, is amplifying a light source, and the light wave is going every time it goes through one of this magnetic structure a little bit bigger. And the electrons are a little bit slower than the speed of light, than the light. And this means that here, this part of the electron bunch produces a little bit light. Here, a part that is a little bit behind produces adds something on this light, and here it's again a little bit behind. And actually, by tuning this lagging of the electron bunch with respect to the light source, or to the light waves, you can tune the wavelengths of the light source. So only if the backlagging of the electron bunch fits exactly the wavelengths when it comes to the next round, to the next magnetic structure, only then it adds something to the light source. If it's not in phase, it's not adding to the light source. And this is how you can tune the wavelengths. And it's a little bit counterintuitive, because, so this is what I already said, but when you have stronger magnetic fields, you have longer wavelengths. Now you would think, if you know a little bit about wavelengths, you will say a shorter wavelength is a higher energy. So why does a stronger magnetic field gives a longer wavelength and not a shorter wavelength with more energy? And the reason for this is that the stronger the magnetic field is, the bigger is the detour the electrons are making with respect to the light, because the light always goes straight on. So this is a light wave, but the light wave is propagating always in a straight line. The electrons, on the other hand, as I showed you before, are doing the zigzag course here. And the zigzag course is the stronger the electric field is, the stronger are the wiggles these electrons are doing. And therefore, they are lagging stronger behind the light source in a longer way and creating longer wavelengths in this way. So a stronger magnetic fields makes longer wavelengths. This means the energy of the wave, the photon energy of the wave is smaller, but it creates more photons. So the stronger the magnetic field, the longer the wavelengths, but the more intensity you actually get, of course. These X-ray flashes are extremely short because the electron bunches are so short. I told you about the 100 femtosecond. That's about what we are trying to reach. And if you are comparing this to the speed of light, for 100 femtoseconds make a laser beam that is only 30 micrometer long. So if you look at the magnet structure is in the order of millimeters. So what you actually have here is you have laser discs. You don't have a beam of laser that is a long part of light or so, but you have a very short, only 30 micrometer long disc of light coming out of these undulators.
I will quickly chime in here, Joachim. There's a question which does fit here. It says, does X-rays wavelength depend on distance between alternating magnetic poles which determine undulating motion of electrons besides relativistic Doppler effect?
Yes, it does. So this is one of the factors. The electrons, if you would have only an undulator without these the Sarze effect, what I just explained, the effect that you have always the right distance or the right difference between the phases, between the path of the electrons and the wavelength. So if you only have an electron wave that is not interacting with the same electron package, then you have so-called synchrotron radiation, which is a little bit different from free electron laser radiation. And in this radiation, you are also tuning the wavelengths by tuning the either the magnetic, by tuning the magnetic field and the structure of the field. So the longer the structure is, the longer this period is between two magnet changes here, the longer the wavelength, the grounded wavelength is you have. And within this wavelength, then this depends also on the magnetic field, but within this wavelength, you can then select with this phase selection, you can select the right wavelengths. But the basis wavelengths, the range of wavelengths you can select from by tuning the magnetic field is actually given by the distance of the magnets and the sizes of the magnets. So smaller magnets create smaller wavelengths from the beginning. That's true. But then, of course, there comes a relativistic effect, and the relativistic effect is the stronger, the higher the energy of the electrons is. So you have actually several possibilities of tuning the wavelengths. And in the flash, the first free electron laser that we had in Hamburg that I showed shortly on the soft X-ray laser I showed shortly on the slide, there the magnetic structure was fixed because one was not quite sure if we can be with these strong automats be precise enough to changing the gap of this undulator. So they had fixed gap undulators, and there they were tuning the wavelengths by changing the energy of the electrons. So just by the Doppler effect, basically. So three ways of tuning the wavelengths. One is by selecting the size of the magnetic structure. The other is by changing the magnetic field. You cannot change the field of a permanent magnet, so we are doing this by changing the distance here. And the third one is by changing the energy of the electrons. And we are at European XFEL, we do both actually, or all three. We have two different kinds of undulators. We have one kind of undulator for soft X-rays, which have a larger structure. And we have one kind of undulator for hard X-ray, which has a finer structure of magnet fields. This is one thing we are using. The second is we have 3 or 4 different modes of operation with different energies of the electrons. So the 17.5 giga-electron volt is the highest energy we can reach, but we are also sometimes operating at 14 giga-electron volts or at 11 giga-electron volts to get other wavelengths ranges possible. And the third way is then changing the magnetic field. And this is what every of these undulator devices can do by itself. So we can have different wavelengths in the different instruments that I will show you later. So now I can get to the last part of my talk. What do we do actually with the X-ray? So I will explain a little bit the scientific instruments. So when we are coming to the XFEL site, this is again the picture I showed in the beginning. And here we have our office building. This is where I'm sitting in the moment. So this is my window. And below this, about 12 meters below the ground, you find this experimental hall. It's about the size of a small soccer field, 90 by 50 square meter, an underground hall. We still have a lot of space in here, but if you're looking at this, most of the space of the floor plan, most of the space we already filled with instrumentation. The picture I just showed was taken from here, from this hutch into this direction. So you saw this empty space here. And we have, as I already said, we have two kinds of undulators, one with a larger magnetic structure. These are the soft X-ray undulators, creating softer X-rays to be brought into these kind of bluish, greenish instruments. And we have two hard X-ray undulators, one producing X-rays here and one creating X-rays here. They have finer structures. The undulators behind this are the same, but their gaps can be steered independently so that we can have in this instrument a different wavelength than in this instrument at the same time. And we are operating in many fields of science, and I can give you just an overview of what the electrons are doing. So we are doing atomic physics in the instrument called small quantum systems, where we are actually looking at atomic resolution of really atomic effects. So very small molecules, even single atoms that we are studying with electrons and everything. Then we have chemistry. This is mostly done in the femtosecond X-ray instrument station, where they have normally a liquid jet of a chemical substance, and they are exciting this with X-rays and looking at all kinds of other X-rays coming out of this to study chemical reactions on the while they are going. So doing molecular movies of molecular optics actions. And then we have an instrument that is specialized on biology. It's called single particles and biology and serial femtosecond crystallography, where the bioimages by the biothings are studied to atomic resolution so that you can see proteins to a resolution where you see a single atom where all these atoms sit. And you can also study dynamics of this to trying to make a movie of how these molecules work. And then we have two stations that are working with material science mostly. One is called spectroscopy and coherent scattering using the soft X-rays. And this is actually a magnetic domain structure that can be made visible with this kind of microscope, where you have a cobalt surface, a little thin layer of cobalt, and you are exciting this or looking at this with the X-ray in a magnetic field, and you can see the magnetic structures, how they develop with change of the magnetic field. And here, this is a materials imaging and dynamics experiment where you can, for example, look into the development of a water beam when it's, for example, heated to different temperatures, and see the difference of the atomic behavior of the water within a beam, for is one example. And then another field is high energy density, a very important field we are working here, where we are studying the very high energy densities of matter, and I will come to this as one example. So I will now go give you only 4 examples of instruments we have, because my time is nearly over. I will start with the atomic resolution. So what do we do? Oh, we also have space for extensions, as I wanted
One
to
quick
mention.
question here, Joachim.
Yes. Yeah.
There is one. Would it be possible to probe electron-phonon interactions?
Electron-phonon interactions. Yes, this is done. This is mostly done actually in these kinds of experiments here are. These kinds of experiments where you are using a laser excitation, for example, to produce a phonon. A phonon is a wave of motion of an atom in a solid state. So you're having a solid piece of matter, and you are using a laser for heating it or doing an electronic excitation, and then you have a phonon wave there. And then with a delay, with a special time between this laser excitation and the free electron laser coming in, you can see how these phonon waves are developing. So this is actually something we are doing. So we can work both on the electron and also on the movement of the atoms. So small quantum systems, I showed you, this is the instrument, the first instrument I mentioned, which is doing the really molecular physics, atomic physics, studying here the decay of molecules after intense X-ray illumination. So they are working with this molecule that is called iodo-pyridine. When I was working as an atomic physicist, I would have thought this is a big molecule, but if you compare it to biomolecules, it's a rather small molecule with only a handful or only 12 or 11 atoms in it. It has this very heavy atom here, iodine. It's a very heavy atom, and carbon and nitrogen are about the same size, the same weight, and then it has this nitrogen ends, which are also called protons because their core only is consisting of a single particle, the protons. And you can, with the free electron laser, you can strip off all electrons, nearly all electrons of this molecule. And what then happens is you still have this ring because our X-rays are so short, our laser bunch is so short that the atoms don't move within this 100 femtoseconds, but the electrons do. The electrons are swept away by the electron bunch, and you are left with a structure of an iodine, 5 carbons, a nitrogen, and 4 hydrogen atoms. Without any electrons, and then they are starting to explode. They are starting to come out, to get out of each other, and then you can actually use a so-called reaction microscope to look at this. So you can see the protons coming. They are the fastest. They are coming first, and you can see all 4 of them coming in a special direction. Iodine, you don't see it goes in this direction, but you can see these 4 hydrogen ions. The reason why you don't see iodine is that you keep iodine only in the same direction. So the iodine is basically the point that says what is your direction, and then you are counting the ions, where are they coming on your photographic plate, and where are they landing. And you can do the same with the little bit heavier devices, nitrogen and carbon. So this is the carbon edge. And then you can combine this, and you can see this is an artistic expression of this, how this molecule explodes and leaves behind this 4 carbons, the nitrogen here, the green one, and the hydrogen, because it's such a light atom that is coming out here. It's spread over a bigger area. So this is what you can do, and this is actually a way of learning how these molecules are behaving and how they are composed together. Another thing, as I already told, biomolecules are large compared with these molecules. What we are doing here is we are doing a diffraction before destruction. So we have biomolecules that are brought either in a liquid jet or one by one into the free electron laser, and then we are collecting the image of this biomolecule one by one, and take a full 3D recollection of how this biomolecule looks like. And also here we are making use of the very short intensity because it's 100, it's very short bunches, because it's 100 femtoseconds. In 100 femtoseconds, the atoms cannot move. So this image is an image of how the atoms were placed before they came, even though the intensity we are using is so big that the biomolecule will explode after this and will be completely destroyed. We will see a picture of how the biomolecule looked like before we hit it. MID experiment, the interesting thing here is that we can go to really ultra high resolution by having a several meter long arm where the detector is on. So the detector is far away from the area where we're hitting it, and the detector can be moved around an axis to look at a tiny spot on the scattering imaging that comes out, and looking at the very tiny details of how the matter interacts and how the matter changes. And this is actually where you would do the electron-phonon interactions. This is how it looks in reality. So you see this this drawing, this model, by this engineering model, looks nearly exactly like what we set up in the lab in the end. And then I promised you to tell a little bit, and this is also the last thing I told. I will give as an example is a high energy density experiment, where we are combining the X-rays we are producing here with as short and also very intense optical lasers for bringing the matter into different states of matter. So we can produce matter that can produce, for example, iron that has the consistency in the Earth core, where the pressure and the temperature is so high that the iron is molten, and it's actually in a state that you cannot produce on the surface of the Earth because you don't have these pressures. And we can even see in the structure of large planets. Large planets are consistent mostly of helium and hydrogen, sometimes a bit carbon, and carbon actually mostly in the core. And they have extremely high pressures in there. And in the lab, in this instrument, with very intense lasers, we can produce for a very short time interval, shorter than a microsecond, we can produce this states of matter here, and we can then use the X-rays to study the states of matter while they are still there before it's exploding, basically. And by this we can look at phase transitions and structural transitions. We can look at materials damage, so do actually also research on material science, and we can look into how the matter is when we are trying to do fusion experiments, so trying to bring the atomic cores so close together that they fuse to a new atom and produce their own energy. We are not doing that in the free electron laser, so our intensity is not high enough for initiating fusion. But the states are close to this, and of course one can learn a lot to this when we are coming to this close connection, strong heating and high intensity of light. So on my last slide, I just wanted to tell you that we are not only this big instrument, but we are also people working at these instruments. We are 551 employees. That was in the end of last year. In December, our human resources group always gives us statistics. We are coming from 63 countries. Guests are here treated like employees. So guests are, as an explanations, guests are people who are working here, but who are not paid by the European XFEL, but by some external institutions like other facilities that are collaborating with us or universities. So we have 551 persons altogether. About half of them are scientists. 140 engineers is the next biggest group, but we of course also have administrative and technical staff that is very important to keep everything going. And yeah, this is my last slide. Thank you for your interest that you were coming here. I hope I could give you some interesting insight of what we are doing, and I'm very happy to ask questions and to answer.
Thank you very much, Joachim. That was very nice. There is actually one more question concerning electron microscopy.
Yes.
Someone said you commented on the slowness of electron microscopy. That is actually because of the slow image acquisition. Nowadays, there are very developed new generation of cameras. And do you think that your statement about this slowness is still true?
It's not entirely true. It's true for the kind of electron microscopy I showed you here. So what I showed you there was a scanning electron microscope. Scanning electron microscopy is slow by design. We are using it anyway because it's very handy. It's very easy to use, and we can make a lot of use of it, of studying our structures before we are using the XFEL on them and after we are using the XFEL on them. So for example, if we are shooting the XFEL on a surface, we are producing a crater and we want to see how this crater looks like and how it's developed. And for this, you're using scanning electron microscopy, and this is slow by design. But you are right, there are electron microscopes that are faster. So we also have a transmission electron microscope, which is really limited rather by the detector, by this by the intent, or by the how fast the detector is. And yes, there are already developments of femtosecond electron sources. And basically, it's a similar technology of what we are doing here. So there you also have an accelerator, an electron accelerator. You're shooting the electrons, and you are converting them not into X-rays. You are shooting them directly on the matter you want to look at. And then if you have fast enough detectors, we also need fast detectors. When you have fast enough detectors, you can do similar timings as we do with the X-rays. What you cannot do that easily is the spectroscopy parts we are doing. I was not telling a lot about spectroscopy, but we are able with the SARSA process and later also with so-called monochromators to select exactly the X-ray wavelengths we want to have, while the interaction of an electron with matter always is a mixture of a lot of different wavelengths. So you always get a mixture because the electron is not completely absorbed by the matter, but it's scattered. And this means it leaves sometimes more, depending on how it interacts. It sometimes leaves more and sometimes less energy in the matter. So you cannot be as precise as with X-rays. This is one thing. The other thing is with electrons, you sometimes get into problems, but I also know that there are people working on getting rid of this effect, but you sometimes have problems if you have too thick layers of matter, that you have multiple scatterings, which are more difficult to analyze than X-rays. I mean, I showed you this first X-ray image by Konrad Röntgen with the hand where you see the bones but not the tissue, and this is because X-rays goes through everything. Electrons would be caught in the first layer of the skin already, so they would have destroyed this hand, and therefore I think high energy and or fast imaging with electrons is something that is important, and this will be important for us, but it's a little bit different technology, and we can do different things with X-rays that you cannot do with electrons. And there are, of course, also things where electrons are better and better suited.
Right. So there's one last question. Somebody asked about strongly correlated electron examples.
Strongly correlated. It's not really my field of expertise. So I'm sure we have scientists here who could answer this better. I mean, we are studying these kind of effects. We are studying superconduction, for example, which is a correlation effect in electrons. So it's a SCS instrument, for example. We are in the moment working on at MIT, we are working on cold fingers to bring the matter we are studying into supercooled states where we have superconduction, and we are studying highly correlated electrons structure. So yes, this is done, but I don't have an example I can just pull out of my slides here.
That is maybe a good thing that people should come to the European XFEL visit here and
a specialized question. I mean, you can actually, of course, reach us. You can send us emails or try to reach someone, and I can try to bring you in contact with one of our scientists who is more specialized in these topics.
Yes, that's a good hint. So if you want to get in contact us, just come to our webpage or contact us via contact@xfel.eu. You will find us if you want to have more answers. And we are already 10 minutes over time, but thank you so much for your interest. So many interesting questions. If there is anything we didn't answer yet, please contact us. Thank you again, Joachim, for your very nice talk. Thank you all very much for listening. We hope you enjoyed it a lot and learned a little bit about what we are doing here. Well, stay tuned for the next webinars in this series. And well, we wish you a very nice day and maybe see some of you at one point here at European XFEL.
Yes.
Bye-bye.
Thank you. Bye.